Hello everyone, I'm Bill Stubbs, welcoming you to the fifth video in my series, Dissecting the Standard Model of Particle Physics. I call this one, The End of Quarks. In this video, I continue discussing the contents of my book, Quarks Missed the Mark, by looking at how the discoveries that the proton is made of pions instead of quarks, and the pions of electrons and positrons instead of quarks, affects the structure of the rest of the baryons and mesons, and what the discoveries mean for the continued existence of quarks. Let's get started. In the last two videos, we found that the proton is likely made of 8 pions instead of 3 quarks, and that those pions appear to be made of electrons and positrons. This creates a serious problem for the standard model representation of the other baryons and mesons. This figure shows that several of the baryons decay down to the stable proton. Many of them do so by emitting a pion to become a proton, while others emit a pion to become a neutron, which then emits an electron and its antineutrino to become a proton. With no quarks in the proton and none in the pions, at the very least, no quarks appear to be involved in the structure of any of the baryons in the figure. For example, as shown, according to the standard model, a down quark in the neutron emits a W- boson to become an up quark that teams up with the other down quark and the up quark in the neutron to convert it into a proton. Even if we assume the neutron is made of quarks, we know the proton isn't. Therefore, the neutron decay scenario depicted in the previous figure is not possible. Knowing that the proton is ultimately a large collection of electrons and positrons, and that the neutron emits an electron to become a proton, it seems more likely that the neutron is just a proton with some extra electrons and positrons in it. Since the electron ejected from the neutron has kinetic energy, it is likely additional electron-positron pairs reside in the neutron that annihilate before the electron is ejected that provides this energy. Bottom line, the neutron appears to be made of pions and electrons like the proton, not quarks. If the neutron is just a cluster of pions like the proton, then since the other baryons decay into either a proton or a neutron by emitting a pion, they too appear to be just clusters of pions. 9 in the case of the sigma, delta, and lambda particles, 10 for the psi particles, and 11 for the omega particles. Since we know the pions they emit are just electrons and positrons and no quarks, none of these particles appear to be made of quarks. Therefore, although the standard model scheme of representing and decaying the baryons provides a way to graphically visualize and manage them in their decays, it does not appear to accurately depict what the baryons are and what is happening to them during the decays. It produces the endpoints of the baryon processes, but uses a meaningless model to represent them and execute their transitions. With the proton and the neutron apparently being made of pions, and the other light baryons, pions attached to protons and neutrons, pions appear to be a fundamental structural unit of baryons. Even for the heavier charmed and bottom mesons, which decay by emitting kaons and d-mesons, a large fraction of the d-mesons decay into either pions or kaons, with the kaons decaying into pions, making pions appear to also be fundamental components of the heavier mesons. According to the electron-proton deep and elastic scattering, the charged pions appear to be made of about 273 particles, 136 electron-positron pairs, and a valence positron or electron, while the neutral pions apparently made of 264 particles, 132 electron-positron pairs. When a charged pion decays, it practically always decays into a like-charged muon and its neutrino, whereas the neutral pion decays into 2 photons. The photons that result from the neutral pion decay occur because the 132 electron-positron pairs that form the neutral pion somehow ignite and all annihilate. However, the charged pions decaying into muons suggest that only some of their electron-positron pairs annihilate. The muon has a mass of 105.66 MeV, which, if it is made of electrons and positrons as the pion appears to be, would make it about 207 particles, 103 electron-positron pairs plus its valence electron or positron. For a pion with 273 particles to decay down to a muon with 207 particles, only 33 of its electron-positron pairs must annihilate, leaving 103 pairs intact. Unlike the neutral pion that exhausts all of its electron-positron pairs once they are ignited, something causes the annihilation of the pairs in the charged pions to stop after 33 have annihilated. The main difference between the two types of pions is that the charged pions have an unpaired valence electron or positron. Somehow, it apparently causes the annihilations in the charged pions to stop after 33 have occurred, or, as we will see later while examining the Kaon, when 103 pairs are left. When the charged pion decays into a muon, the muon's neutrino also appears, a neutrino with the positive muon and an antineutrino with the negative muon. When that muon decays, just moments later, the antiparticle neutrino to the one that appeared with the muon during the pion decay appears. One way to interpret this sequence of events is that when the number of pion electron-positron pairs annihilate down to 103, a muon-neutrino-antineutrino pair is produced. Pions with a valence electron capture the neutrino to become a negative muon while letting the antineutrino go. Pions with a valence positron capture the antineutrino to become a positive muon with the neutrino escaping. Since the muon-neutrino-antineutrino pair appears when a valence charge is present, but not when there isn't one, indicates the charge causes the pair production. Since it occurs with either a positive or negative valence charge, the polarity of the charge does not appear to be a factor in the production. In both the negative and positive muon cases, the electron-positron pairs left over from the pion decay continue annihilating after the neutrino or antineutrino is captured until only the valence electron or positron is left, at which time the captured neutrino that formed the muon escapes. In the standard model, kaons are called strange mesons because they contain either a strange or anti-strange quark. The charged kaons pair them with up and anti-up quarks, and the neutral kaons with down and anti-down quarks. About 72% of the time, a charged kaon decays into a like-charged lepton and its neutrino, with 67 of the 72% producing muons. The other 28% decay into either 2 or 3 pions. That the kaon can decay into a muon, like the pion, suggests that its structure may be similar to that of the pion. However, since the charged kaons can decay into multiple pions too, seems to suggest that they are just clusters of pions, like smaller versions of the baryons. Which, if either, is it? The neutral kaon may provide the key to resolving this dilemma. There are two versions of the neutral kaon, K0 sub L, with the L indicating that it has a relatively long lifetime, and K0 sub S designating a relatively short lifetime. The different lifetimes reveal the two types of neutral kaons have different structural configurations, which is also indicated in their decays. The K0 sub L kaons decay into a lepton pair and an oppositely charged pion 2/3 of the time, while the K0 sub S kaons decay into 2 pions more than 99% of the time. The other 1/3 of the K0 sub L kaons decay into 3 pions. This makes the K0 sub S appear to be a cluster of pions like the baryons, and the K0 sub L a collection of electron-positron pairs like the pion. Note that a large fraction of the K0 sub L group decays into multiple pions like the K0 sub S group. This probably occurs because these K0 sub L kaons have the same configuration of the K0 sub S kaons, but a lifetime close to that of the K0 sub L, so they were placed in the K0 sub L group. If that is the case, then the K0 sub L group decays like the charged kaons. Some produce leptons and some pions. Therefore, the charged kaons likely take the two different decay paths because they, too, are different configurations. However, because they have about the same lifetime, they are not distinguishable. They are like the K0 sub S kaons lumped into the K0 sub L group because of their lifetimes. The mass of a charged kaon is 493.68 MeV, which is about 967 free electron masses. Therefore, perhaps one configuration of the charged kaon, call it K sub mu, is just a larger version of the pion containing 483 electron-positron pairs instead of 136 like the pion. Now, like the pion, when the electron-positron pairs ignite and begin annihilating, they continue until only 103 pairs are left, like the pion. Then, along with the valence electron or positron, they produce the muon neutrino-antineutrino pair that leads to the formation of the muon. The second charged kaon configuration, call it K sub pi, appears to be a cluster of 3 or 4 pions. This kaon is the one that decays into 2 or 3 pions. Now, the K0 sub L kaons that decay into leptons look like K sub mu kaons, and the K0 sub S kaons that decay into pions look like K sub pi kaons. The K0 sub L kaons that decay into pions look misplaced if they are characterized by their structure and should be considered K sub pi kaons. Since the pions are known not to contain quarks, and the kaons appear to be either clusters of pions like baryons or just larger versions of the pion, the kaons do not appear to be made of any quarks, just electrons and positrons. However, because of their decay paths, there does appear to be at least 2 different configurations of particles that are called kaons. In the standard model, the heaviest mesons are the D or charmed and B or bottom mesons. As their names imply, they are mesons that contain charm and bottom quarks in addition to up, down, and strange quarks. The charged D mesons are supposedly combinations of charm and down quarks, and the neutral D mesons, charm and up quarks. The masses of these mesons are 1,869.65 MeV and 1,864.83 MeV, about 3.78 kaon masses, and they mainly decay into kaons, pions, and leptons. This suggests that the D mesons are 4 kaons bound together by sharing electrons and positrons. That would also make the D mesons 16 pions. There are also charmed strange D mesons that are combinations of charm and strange quarks. These mesons also decay into kaons, pions, and leptons, but are about 100 MeV heavier than the charmed D mesons, so they are almost exactly 4 kaon masses. To allow for binding, this makes their mass look like 4 kaons and a pion bound together. Since the D mesons decay into kaons, pions, and leptons nearly all the time, they appear to be made of pions and kaons. Therefore, based on this and the previous discussions of pion and kaon structure, the D mesons do not appear to be made of quarks. There are 10 B mesons in the standard model that pair the bottom and antibottom quarks with the up, down, strange, and charm quarks and their antiparticles. The B mesons are extremely heavy particles, with the charged B meson having a mass of 5,279.33 MeV and the neutral 5,279.64 MeV, or about 2.8 D meson masses. There does not appear to be a dominant decay mode for B mesons, which suggests that their components are loosely bound. When they decay, it is mainly into one or more D mesons with kaons, pions, leptons, and even some baryons, which suggests that B mesons are made of at least 3 bound D mesons. The bottom strange B sub S mesons are 5,366.88 MeV, also about 2.8 d meson masses. They too decay into d mesons, kaons, pions, leptons, and baryons, and appear to be 3-bound d mesons like the charged and neutral B mesons. The mass of the bottom charmed B sub C meson is 6,274.9 MeV, or about 3.4 d meson masses. They also decay into d mesons, kaons, pions, leptons, and baryons, which makes them look like 3-bound d mesons and a kaon. The B mesons decay into d mesons, kaons, pions, leptons, and baryons, which all appear to be ultimately made of electrons and positrons, not quarks. There are no top mesons. So, since B mesons decay into D mesons, and D mesons into kaons, and kaons into pions, it appears, as is with the baryons, the fundamental components of mesons are pions, which are just collections of electrons and positrons. No quarks are needed. With no other role in nature, this seems to show that quarks apparently do not exist. In the upcoming videos, we will examine the structures of leptons and show how they are also the products of pions.